Okay, so we are now in lecture 7, still about MOS transistor theory, but we are approaching to the end of device related stuff. So maybe this is the final lecture for device related concept. So in the previous lecture, lecture 6, we have thought about long channel IV characteristics. So input and output characteristics were studied, and at the time I told you that we have to draw these two figures like ID versus VGS for certain VD values which is quite small, close to 0. Also another one which is VDD. So in this case, we must draw both linear scale and logarithmic scale. So we will draw, and another one is output characteristics. In this case, still ID is drawn, but the x-axis is not input voltage, but output voltage VDS is used. Of course, when we have very low gate bias, then current will not flow. So this is for low VGS case. However, if we increase gate voltage beyond the threshold voltage, then we will have such kind of behavior. That will be the output characteristics. So both of input and output characteristics are quite important, so you must draw both of them. After that, we have thought about capacitance. So capacitance, there can be many components. Of course, most important one is of course oxide thickness, and that is determined by actually effective oxide thickness. Yes, this is the main one. This is really wanted one. However, we have unfortunately other parasitic capacitances. So if we have gate, and here we have source and drain. So we have a certain capacitance and another capacitance between source and gate and drain and gate. Yes, this is the one. And another one is here we have body contact, and in planar MOSFET we have usually N plus P junction in the case of N MOSFET, or sometimes P plus N junction in the case of our P MOSFET. Anyway, in every cases we have the device or the PN junction in its equilibrium or reverse bias case. So when the PN junction is placed in its equilibrium state or reverse bias condition, it does not conduct. So there can be good isolation, electrical isolation between these two parts, so-called source and drain and substrate. But here we have capacitance. So that capacitance should be also considered when we consider time-dependent propagation of a signal. So that was one thing we have to keep in mind. And this kind of diffusion cap. So diffusion here means that why we call it as a diffusion. This is related with source and drain region, because in historic reason, in the former times we have made source and drain region with diffusion process. That's the reason why still it is called as a diffusion region. And anyway, here we have diffusion and plus diffusion and p type substrate, and we have capacitance. But capacitance can depend on the two things. One thing is, yes, this main body of your diffusion and side part of your diffusion area. Both of them contribute to the parasitic capacitance. So this one is corresponding to area dependent one, and this one is related with the perimeter dependent one. Okay, so that was the first part of our previous lecture. After that, we have thought about non-ideal IV. When we say non-ideal IV in this course, it is simply means that short channel effect. So that is the most important one. Short channel effect means that at every technology we have the minimum LG value available. Yes, so for example, if we are talking about 65 nanometer technology, then more or less in this case it is 50 nanometer. And we are now, where are we now? We are around the age of 3 nano technology, and the minimum channel length is about 14 or 12. So that is the values around the minimum number for our minimum bit length. So in this case, the characteristics of this minimum size or shortest channel length device is far much different from that of long channel device. So that's the reason why we have to consider some special cases where channel length is quite short. So however, unfortunately, we have not covered all of them, just covered the concept of on current and off current. Do you remember? So on current means that the current ID at VGS and VDS equal to VDD. This is the maximum current we can conduct inside this transistor, and this is just to determine the speed of your system. So if this ID is high, then when the capacitance is given, then you can easily charge and discharge the capacitor. So that's the reason why you can have high speed system. On the other hand, we have another quantity like off current. This is corresponding to VGS equal to 0, but VDS equal to in this case VDD. So basically, since the gate voltage is 0, in ideal case we must have 0 current or extremely small current. However, drain is biased to VDD, so although our channel says that, our gate says that, okay, nothing, but here we have VDD, which is just to attract our electrons from here. So if this drain voltage is too high, then even though the gate does not allow the current conduction, there occurs current conduction. So this is really unwanted behavior. So this is called as leakage current, and this off current is the representative leakage current. So we must consider both of on current and off current. The ideal case is very high on current, at the same time very small or very low of current. That is the ideal case. So if we consider this very ideal case, then what will happen? So if we consider this idealized case, then please draw your input characteristics in a semi-logarithmic scale, please. So everybody, so please do your exercise, not just watching my drawing. So please try to draw your own one. So what is the input characteristics? This is drain, and this is GS. This is the one, and both of them, so I on and I off, are drawn when VDS equal to VDD. So we can draw only one graph, and here we take logarithmic scale. Then what is the difference between on and off? On condition is here we have VDD, and off condition here we have 0. So in ideal case, please try to your desire. Where do you want to have the on current? Do you want to have on current here or there? Which one is preferred one? Of course, in this scale, this one is much better. You want to have very high. So wait for a while because my pencil is stuck once again. Okay. So this is desirable. In the case of off case, where do you want to have it? Here or there? Obviously, you want to have this low one. So in an ideal case, if you want to have a very good transistor, your semi-logarithmic input characteristics looks like this, and some curves in between. You must have a certain curve connecting these 2 points. So ideally, the best way is maybe this one, very steep curve, and after that, beyond the threshold voltage, you have a certain values for your on current. That is desirable. So now you may understand this slope is important. If we have steeper and steeper slope for this part, then when the off current is given, then we can increase it and reach the required on level quite easily. After that, since there will be certain current, so if we have this kind of condition, then we can reduce our VDD value. As I told you before, lower VDD value is always desirable in the mobile era, so we want to reduce this value as much as possible. But you know, at the end of our previous lecture, I told you that this slope in this semi-logarithmic scale, there is a limit. So we cannot make any further steeper than this rule given by our nature. Okay, so I will explain later. So I prepared another graph. But anyway, that was our previous lecture. So therefore, it is obvious that this condition, very high on current and very low off current, is not possible to be met simultaneously. Therefore, we have introduced various device options which is related to the high power. High power is more concentrated on maximizing the on current, or low power. Low power is more concentrated on lowering the off current, and we can also think about standard one, so more balanced one. So now let's go to our next slide. So previously we have thought about Intel's 32 nanometer transistor, and this is also similar one taken from 22 nanometer. So 22, yes, so this is 22 transistor, and you can see that here still we have high performance and low power, and now you can see that, oh, there is one more corresponding to ultra low power, and nowadays you find that there are more and more options because nowadays improving device technology is getting more and more difficult. So instead of improving the device technology itself, but technology guys provide some more options to the designers. Okay, although we cannot improve drastically, but I will give you many options. Please use one of them to optimize your system. So you can see that all of them has VDD, 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 quite similar values, and you can see that also here same gate length. So gate pitch is corresponding to the gate length, so not exactly gate length, so multiple of gate length. So basically they are the same devices, so you know that they are similar values, and you can see that this is N MOSFET and IDC. What is it? This is corresponding to yes, this number, this number, and this number. That is number of your ion value. So you can see that ion value is, how large is it? So this is 100 nanometer per unit length. Also they have the same length, but please note that this is in the case of milliamp scale. So 1.808 milliamp per micrometer. This is ion current, and I of current was set to be 100 nanometer. So 100 nanometer is 0.1 micrometer. So are you with me? So from this one, high performance case and this case, then what is the ratio between ion and IO? You can immediately find that the ratio is just around 10 to the 4. Okay, so are you with me? So 10 to the 4 is the ratio for high-speed logic, high-performance devices. Then please have a look at this one. In the case of low-power case, let us calculate also ion over IO. Ion, its value is 0.41 still milliamp. And here we have 30 picoamp. So are you with me? So in this case, this is 10 to the minus 12, and this is 10 to the minus 3. So we have 10 to the 9 times 30, 41. So we can have more and less this number for 10 to the 9. So you can immediately find that the number is corresponding to about 10 to the 7. So you can see that when you have a high speed or high performance device and low power device, although your own current is increased by factor of 2.5. So from 0.4 you have around 1, so 2.5 times increase in your own current. However, you can see that increase of current is about 3,000. That's the reason why you have a drastic reduction of on-off current ratio. Okay, so now you have a very poor, relatively poor on-off ratio. However, you get more powerful device when it is fully turned on. Okay, so also you can understand here 40. Here you have 30, 34, 34, and 40 means that if you wanted to have lower leakage current, then you must increase this gate length. So gate length, I mean that we are now talking about the current between this and that. Here we have a source and drain. Although gate does not allow the current conduction. This is the situation for your minimum sizes devices. But let's think about this one. Now your source is placed here, and now your drain is placed here, and your gate is controlling over this longer length. Then what will happen? You can easily understand or guess that the leakage current between source and drain can be drastically reduced when you have a longer channel length. Okay, because the physical origin of this leakage current is just the proximity between source and drain. Although gate try to cut them all, however, since drain is too close to source, so it also have a certain impact on source channel's electrons movement. Okay, so if the drain is far away and this part is solely controlled by only gate, then leakage will be reduced further. Okay, so now you can see that although we have a slight increase of to about 20 times a longer channel length, and we can see that op current is drastically reduced by factor of 2. Okay, so now let's this up to now we have just think about what should be measured or quantified, and you can see that the most important one are on current and off current, or this is two important metrics. And also we must consider input characteristics and output characteristics of our transistor. These are important ways to characterize our MOS transistors. Then now we will see why we must or why we have this kind of performance reduction when we consider our short channel transistor. Okay, so then before talking about that, so let me just come back to our slide. Okay, so well, how can I delete this one? Okay, so this is gone. So you know that once again, please have a look at this one. Here we have a black curve which is corresponding to our ideal IV characteristics, or sometimes more frequently long channel IV characteristics. And here we have blue curve which is close to the measurement data, although that is not exactly measurement data, but that is quite close to that measurement data. Okay, then once again we can find that the first thing we have to keep in mind is when we have such kind of realistic transistor, we have reduced current level. The current level so predicted by this point, this BD on current is much lower. Not only this saturation current is reduced, but also please think about this part. Here we have curves for linear mode and linear mode. They are biased with the same gate voltage VGS equal to 1.0, and now we have different slopes. What does it mean? Do they have a different width? No. Do they have a different length? No. No. They have all the same parameters. And how about their expression? So for example, VGS minus VT. Is it different? No, they have the same threshold voltage and they have same gate bias. Okay, also they must have something like this minus VDS. However, VDS is also same because VDS here, this is the same VDS and VDS. So everything looks perfectly identical. However, we have here and there different slope. What is the physical origin of this reduction observed in linear part? That is corresponding to our mobility. That's the reason why my today's lecture starts from mobility degradation. So mobility degradation, usually when we consider the ideal long channel characteristics, we just consider mobility as a constant, for example 500 or 200. So in many exercise homework problems, you will see the constant value. But unfortunately, the mobility is a severe function of vertical, so I made mistakes, vertical electric field. So what is here vertical? Then what is lateral? So please have a look at this diagram. Usually, although we are now in the era of three-dimensional transistor, still sometimes we draw in this way. Here we have a source and drain and gate. Even in this course we are doing in this way, although our transistors are fabricating in a little bit different shape. But anyway, in this case, what is vertical and what is lateral? So in the textbook, when we say lateral, this is the lateral direction. And what is the vertical? Then now you can understand this is vertical. So vertical means that simply the direction for MOS. So the vertical E field here means that the electric field from gate to our channel region. So that is the vertical electric field. Simply speaking, when we have higher and higher vertical electric field, then the answer is mobility of holes and electrons. Both of them are reduced. That is quite a simple rule. So are you all with me? So simply speaking, I can move to the next one. So maybe okay. This is so very soon we will discuss it about later, but simply speaking, when we increase vertical electric field, then our mobility is decreasing. So when we have a higher electric field, mobility is decreasing. So therefore always our mobility curves looks like this way. Then please try to consider what is the direction of your gate voltage. So up to now we have thought about electric field, but how about gate voltage? In the case of your N MOSFET, the direction of increasing electric field is exactly matched to the direction of increasing gate voltage. So when you give the transistor higher and higher gate bias, then you collect more and more electrons. That's good, but unfortunately your mobility, electron mobility, goes down. So please note that both of them are contributing to our drain current. In which way? So we have COX and something Vg minus Vt, that is corresponding to our electron density. And when we have higher and higher gate bias, we have more and more electrons, but also we have mobility, and this is another proportional component. So simply speaking, they are competing to each other. So that's the reason why, although we are not that much interested in this digital course, but when we calculate the quantities called as GM, transconductance of our transistor, although when we increase gate voltage, then although we have always ever increasing drain current, but when we draw the first derivative of our drain current with respect to this gate voltage, then the figures just looks like this one. So here we have the steepest slope. After that, the slope is degraded and we have this kind of behavior. So in analog scene, so this is quite important because this transconductance is very important to maximize the gain of our amplifier. So this point. Why do we have this kind of behavior? If mobility is constant, then we will have just a flat line. However, since we don't have constant mobility, since mobility is degrading when we have higher and higher gate bias, then that's the reason why we have the peak value, which is sometimes biased for our amplifiers. Okay, so let me just come back. We will discuss it soon after. So my caution on this textbook example is this is just one realization of one possible example of mobility dependence on gate voltage. So please do not believe that this is fundamentally important and nobody cannot change these numbers. Wow. How about 90? Can you make it? Yes, sure. So it really depends on your device. So this is just the empirical expression for your device. There are many different data, and this is just one good example. So please do your exercise at your dormitory room. So please do your exercise, because in this case you can just insert your gate source voltage and oxide thickness, then you can calculate the reduction of your mobility. So this specific form just says that when your gate voltage is not that sufficiently high, and when your oxide thickness is quite high, thick oxide and low gate bias, then actually this term does not contribute much. Also, this term does not contribute much. So are you with me? So simply speaking, these forms are written as this form. Mu effective mobility is given by certain mobility value and 1 plus something, and this something is increasing when you have higher and higher gate voltage. So let's say that you have a very low gate bias condition. Then what will happen? If you have a very low bias condition, then your this term, shaded term here, or shaded term here, does not contribute. Then what will happen to your effective mobility term? Then it will just reduce to mu not shown here, 540 and 185. And is it the fundamental value? No, certainly not. There is no way to treat them as a fundamental value, but please note that more or less you can find that mobility of electron has the low field values about 540 and 185, so there is huge difference, about 3 times difference in their mobility values. Okay, any question? So please feel free to. Okay, so here you have oxide thickness effect here. This is electric field, and here we have oxide thickness. So when we multiply both of them, then we will have a certain voltage scale quantity, and here we have voltage scale quantity. So voltage divided voltage gives us a unitless quantity. So this is just a mere number. So we have the number, and it means that if we have a thick oxide, let's say that if we have a thick oxide, then this lower part becomes a large number. So it means that now our same amount of gate voltage increase becomes quite a small impact on our mobility reduction when we have thicker oxide thickness. Okay, simply it is quite simple. Let's just think about this one. That is a good question. Now think about this one. Let's say that there is only 1 nanometer thick oxide, and let's just think about there is 6 nanometer thick oxide, and you change it additionally 1 additional volt, and you apply 1 additional volt. Then please try to estimate increase of your electric field. How much electric field you will get out of it. So yeah, so you can easily understand more or less. I mean that this is just a rough estimation, but the value will be about 1 volt divided by 1 nanometer. And in the case of this one, what will be the rough estimation for your electric field increase? In this case, 1 volt divided by 6 nanometer. That will be appeared. So then how much is the difference of their magnitude? Roughly 6 times difference is obtained. So simply speaking, when you have 1 nanometer oxide and 6 nanometer oxide, although you increase 1 volt in this expression, your 1 volt increase of gate voltage is just underrated when you have thicker oxide thickness. Okay, so that is obtained here. And then since all of you don't have any question to me, then I'll give you a question. Please compare this N MOSFET expression and P MOSFET expression. Then please try to find out something. What is the difference? What is the visual differences between? Here you have it, and also, do you have any other? Of course, here we have some difference numbers, but yes, both of them are just marginal one. So please give me your definite answer. So yes, you are right. That's it. That is important. We have the power, which is close to number 2, and here we have power, which is close to actually exactly to 1. So the last statement in this slide just asking this question: why do we have different behavior for electrons and holes? That is because although electrons and holes in the case of silicon are well balanced compared to other materials, however, even in this silicon case, electrons and holes have different internal structures, like called as band structure. Band structure of silicon's electron and silicon's holes are different. That's the reason why we have different power here and there. So that is originated from the band difference of band structure and scattering mechanisms. Then now let's go to the real data. So this data is quite famous. So this is quite famous, and this graph was been quite famous for a long time. So please remember its nickname. Its nickname is Universal Mobility Curve. So Universal Mobility Curve means that, so I'm not kidding. So in several decades ago, so researchers in the world collected data from different fabs. So it means that there is American fab and Japanese fab. At the time we had a well-known fab, and there is a European fab. Then they fabricate their own best devices. Okay, and the researcher, Japanese researcher at the time in America, collected them all and tried to draw a graph, which is x-axis is magnitude of electric field and y-axis is mobility of their transistors. And what will happen when the researcher draw the curves from Japanese fab, American fab, European fab, they found that all of them are just drawn as this curve for electrons, and all of them are drawn in this curve in holes. That was experimentally discovered. Of course, that can be supported by our theory, but they have demonstrated that that is really possible even 90s, so several decades ago, that was possible. So this is called the universal mobility curve. It means that if you do your best, the human beings best, then you will get this kind of graph. So if your device shows, for example, this number for your atmosphere, it means that you have something to do further to improve your performance. But if your device is showing this number, then it means that there is no further way to improve something. So this you are doing quite well and quite close to the limitation of human capability. So this is mobility, universal mobility curve. So this curve is this course is not for device physics, but for circuit designers. So simply we just accept this concept, and I will finish this discussion with the physical origin about this specific behavior. So you know that previously, electron and holes have a different power. Then this different power can be supported by this different graphs. So here you can see that electrons shape. Oh, you can see it quite clearly. So electron has this steep rollover. And how about here? For same electric field, for example 1 megavolt per centimeter, then how about your whole graphs? This is the graphs. So this is corresponding to different power shown here and there. Electron has silicon electron inversion layer shows much faster mobility degradation when we have a high vertical electric field. And why? That is due to the difference of band structure. Okay? So, and another one we can say is, okay, electrons and holes, they have quite much difference in their mobility value. Usually electrons has much higher values. So how many times? This is about 200 and this is about, wow, this is about 800. In this case 4 times larger. And how about this one case? This is about 60 and this is about, well, this is about 200 something. So no, there is also still 3 or 4 times difference in their mobility curves. Okay, so electromobility is much higher than hole mobility. But please note that much higher in this course means that only for silicon. When we consider other types of devices, so-called 3-5 devices, they have orders of magnitude different mobilities for electrons and holes. So silicon is quite well balanced devices. And if you have a look at this one, then obvious question is like this. Well, please have a look at this one. Compare these numbers. Can you find 3 times difference in NMOS on current and PMOS on current? So please note that in this graph or in this table, the leakage current is fixed. So both of MOSFET and PMOSFET have the same up current level. Then we expect that since mobility of electrons are much higher than mobility of holes or p-MOSFET, we expect much higher value for n-MOSFET. This is the textbook material. Even in our course, we will say that electron has a much higher mobility. So when we draw our MOSFET and PMOSFET should be drawn somewhat wider to match the balance of their performances. But please have a look at this 22 nanometer technology. So you can see that although PMOSFET has a relatively lower value than NMOSFET, but the ratio is not like 2 to 1 or 3 to 1. The ratio seems to be about 10 to 9 or 10% higher or 20% higher. What is it? So this is related with other effect called as stressing effect, but we will not consider this one in this introductory course. But please have a look at is it still true that PMOSFET has a lower current? And always we must care about PMOSFET because PMOSFET has a lower performance, so in order to boost it, we must widen one. However, as technology evolves, the technology gap between MOSFET and PMOSFET is not that severe than the textbook example. Okay, that is one thing. Okay, so up to now, I have spent quite a long time about what will happen if we increase gate voltage. So what is your lesson for this course today? When you have a higher gate bias, the mobility will decrease significantly and rapidly So we will have degraded values for your drain current. That is one thing. So instead, now we understand why we have this kind of behavior. However, there is another one. Still, we have quite much differences in the saturation level. So maybe you can say that, okay, since mobility is reduced here, so it impact on the reduction of saturation current. Yes, that really affects something. However, this is not uh, the only one. So please have a look at this graph once again. Previously, I told you that the transition point of this ideal IV characteristics, and I told you that if we just uh, connect these transition point, then more or less we will have a parabolic behavior. Okay, so are you with me? So because the saturation current is proportional to this gate over square of gate overdrive voltage and this point. So the transition between linear and saturation mode is given as VGT, gate overdrive voltage. So that's the reason why we had a parabolic case. However, in the case of a short channel MOSFET, these blue curves, then things were a little different. I mean that here, although it would be not that easy to determine the exact point for transition, but maybe somewhere here, and maybe somewhere here, and maybe somewhere here, we have the transition point. Here and there, it looks okay, but here we have just a straight line, and it's not increasing, steep enough. So what is it? Or let me just explain a little bit more. So when you measure the difference between this saturation current, wow, that is huge. And when you measure the difference this and that, this is reduced, and this and that, this is even smaller. However, when you have a look at this short channel effect, short channel case, then you can find that this difference and this difference, the difference of your drain current due to the change of your gate voltage is somewhat similar between two different gate voltages. So why do we have this one? This cannot be simply explained by this mobility reduction. Of course, overall, the reduced value of your drain current can be affected by mobility. However, that does not uh, explain everything. So we have to consider linear increase of saturation current. So today we will talk about this second issue. Okay, this second issue is originated from the phenomena called velocity saturation. So velocity saturation means that it's like a raindrop. So yes, this is ground. Here we are ground, and yeah, then there is a cloud, and water drops are falling. So then, what will happen? We have constant acceleration called as geometric gravity acceleration. Then what will happen to this water drop? So is it becoming super fast? So after that, if that is sufficiently accelerated, then we have to hide when it rains, because it will become super dangerous to everybody. So even however, Nobody just hide from the rain because it has limited value. So speed of your raindrop is just saturated and velocity not increasing any further. Why? Because there is air, and this air gives the collision between this water drop and air molecules. So there is some speed limitation. It's like this phenomenon. You have electric field. Electric field is working as a accelerating driving force. You are accelerating your electrons and holes and expecting that when you have lower value or higher value, then if your acceleration is higher, then you expect higher and higher electron and hole speed. This figure shows this behavior. Means that when you increase your electric field, then the terminal speed of your electrons and holes are increasing. So these blue curves are realistic curve and increasing, and eventually it is saturated. So saturated value is more or less having the value of here 10 to the 7. Please remember this number, 10 to the 7 centimeter per second. This is the saturation velocity of your electrons and holes. Of course, they have a little different values, but I think that it's okay just to remember 10 to the 7 centimeter per second. So how fast is it? So please remember that this is corresponding to 10 to the 5 meter per second. And what is the speed of light? Speed of light is 3 times 10 to the 8 meter per second. So the speed of your electrons and hole is about just 1/3000th of light speed. So this is sufficiently low speed to eliminate any kind of relativistic behavior. So anyway, this is the speed of your electrons at most. So simply speaking, when we increase the drain voltage, think about what will happen. Here you have certain gate length, and here you have a grounded source, and here you have VD biased drain. Then what is the average electric field between, the average between source and drain? That will be not that difficult. VD, voltage difference, divided by LG. So are you all with me? So this would be about average electric field. So if you increase your electric field, or if you increase your drain voltage higher and higher, then your electric field will increase. So it means that now starting from 10 to the 3, oh sorry about that, starting from this number 10 to the 3, this is usually written as 1 kilovolt per centimeter, then you have a certain value. Okay, now let's think about this one. Now you are moving to 10 times a higher electric field, 10 kilovolt per centimeter. Please estimate what will happen to your electron's speed. So since the acceleration becomes 10 times faster, so the terminal speed of your electrons will be more or less 10 times. You expect this guy. And how about the realistic one? It follows such kind of behavior, and at the end of this journey, it shows a slight degradation. Okay, 10 times higher electric field does not give us 10 times faster electron, but more or less 7 or 8 times faster electron. Then please consider this one once again. Now we increase the electric field 10 times further, 100 kilovolt per centimeter. Then do you expect 10 times faster electrons? Unfortunately not. The speed is saturated, and this saturated value is about 10 to the 7 per second. So now you can expect that there is one effect. Okay, when you draw your output characteristics, you draw this way, VDS and ID, and your curve, the realistic one, shows this behavior, and you have the linear and saturation mode, even in the case of your N MOSFET. But in the case of this Schwarzschild device, then what happens is when you have we start from a little bit degraded slope because due to the mobility degradation in the vertical electric field. However, before reaching this point for long channel IV characteristics, what happens if our electron speed is saturated? Then let's say that this is the original expectation from long channel 1, but before reaching at this point, let's say that velocity saturation effect occurs a little bit earlier. Now velocity is no longer increased, although we increase drain voltage. Then now we will have just early saturation, then this long channel behavior. Okay, so are you with me? So let me just repeat once again. Long channel characteristics also have current saturation, but this is not related to the velocity saturation. However, there are two different computing mechanisms. One is that of long channel MOSFET, and one is velocity saturation. If this velocity saturation occurs earlier than so-called pinch-off effect of long channel MOSFET, then we will get earlier saturation of this IV characteristics. So let me just come back. When you have a look at this long channel behavior and this short channel behavior, then you can find there is some differences in saturation voltage. So if we just follow the behavior of a long channel MOSFET, then we must wait until about, for example, 0.6 volt to have eventual current saturation. This is nothing related with velocity saturation. But you know that here we have early saturation. Why we have early saturation? This is not related with the pinch-off effect. So the mechanism used in the long channel MOSFET, but this is velocity saturation limited behavior. So from beyond this point, our electron velocity is more or less the same, reaching at 10 to the 7 per 7 centimeter per second. So that's the reason why we have velocity saturation. So are you all with me? So the major difference between long channel and short channel. Yeah?
저기서 밸런스 딱 고정되는데 증가 왜 더 증가하는 건가요?
Oh, that is a good question. Thank you. However, that is also another one. We will discuss it later. So if we have only velocity saturation, then there will be just a perfectly flat line. But you know that here we have a finite increase of current, and this is related with the so-called channel length modulation effect. Okay, so we will talk about it later. Oh, instead of it. So I think that here some of you already heard about channel length modulation, and unfortunately some of you have not. So I will explain it right now. So instead of postponing considering this channel length modulation, let's say this one. We are now considering extremely short device. So short device, now here we have source and drain. Here when we have a certain gate voltage, we will have a lot of electrons, so many electrons. And how about this one, this point is important. When Vd equal to 0, compared with this source end of your channel, the number of electrons collected in this part will be the same. Okay. However, if you increase drain voltage, then the number of electrons in this point is now less than this point. So usually people draw in this way. At the beginning, there are same amount of electrons. So here we have the same amount of electrons. So thickness of this blue shaded layer just represent the number of electrons. And when we increase higher and higher drain voltage, then now we have lower and lower electron at this drain side. Why do we have lower number of electrons in this part? It is because the number of charge at this X point at electron was given by Cox times Vg and channel minus threshold voltage. No, here we have a channel. Channel voltage and gate voltage, their difference is important. However, in this source side, it is always biased to 0 volt. Good. But when we have higher and higher drain bias, then this drain voltage affect the channel voltage of your drain end. So now when your drain voltage is sufficiently high, then what happens is now you have no more electrons at this point. Then later what happens if you apply further and further even higher drain bias, then I mean that starting from here, if you increase even further voltages are applied, then this part now entering into so-called subthreshold region. There is no longer any electron error. So simply speaking, following this analogy or this discussion, so in the case of this quite high drain voltage case, then let me just draw much better. So please, in this case, if I draw the distribution of our electrons, then it will be like this. Here we have electronic channel, and here we have no further electrons error. Then maybe the natural question is, okay, professor, here we have no electron error, but how can we have the current conduction? This is just disconnected, electrically isolated. No, it's not. So here we have a really high electric field. Although the number of electrons is extremely small, they can move quite fast in this region. So that's the reason why, compared with our previous case, I mean that low gate bias case, we can have still current conduction. So then, now compared with this point, think about this another case. Now we just have this kind of behavior. Electron channel diminishes or disappears at this point, or electron channel disappears at this point. In this case, the channel length can be represented as exactly Lg. However, if we have the end of actual channel at this point, then instead of this full channel, we have to have a little bit shorted channel. Okay, so are you with me, Mr. Kang? Then, our drain current is proportional to W over L ratio, and this L is not actually the drawn channel length, but it should be regarded as effective channel length. The actual physical channel, electronic channel, or hole channel underneath the gate region. So since this channel length is reduced, the lower part is reduced, so now overall current is increasing. So that's the reason why here we have finite non-zero slopes in this part. So this finite slope is attributed to so-called channel length modulation effect. So channel length modulation effect simply means that this happens.
길이가 짧아지니까 저항이 작아진다고 봐야겠네요. 코너의 길이가 작아지니까 저항이 작아져서 전달하고.
Okay, so you're right. So it's like the device which has, you can simply understand this one as the characteristics of the device whose source or whose drain is much closer than the drawn length, so your current becomes higher. Okay? So you are right, your question is right. So that is channel length modulation. So let's come back. So thank you for your good question, and if you have further question, then before come to me, so please check the contents like channel length modulation. It is repeatedly explained in many places in, for example, microelectronics course or semiconductor device course. Please review those contents, and I can give you further answer to your question. Okay, so now let's come back. Now already we have only 2 minutes left, so it's pity. So velocity saturation effect. So today my original plan was to consider a simple model about this velocity saturation. So unfortunately, I spent quite a long time about explaining details of other stuff. So in the next lecture on Thursday, I will explain it, this part. Okay, so sorry about this slow progress of our lecture course, but in our class, we have quite a variety of this academic background, so we have to explain a little bit detailed way about background material. So in the next lecture, we will consider the analytic model for velocity saturation. Okay, is there any question from audience? No? Okay, then let's wrap up today's lecture.